So today we're finishing our discussion of the Hausdorff series converging in an ultrametric space. Our first topic is groups defined. Group, I guess, is just the one group defined by a complete normed Lie algebra. So we're going to let H be our Hausdorff series with components R, S, multi-graduation inside of L hat over two indeterminates, you know the drill. Hausdorff series. We will show that the corresponding formal power series with continuous components, and this is we're going to show that this is convergent. H tilde sub R comma S inside P hat of G times G on G. I show it's convergent. Alright. So I guess it's not an immediate proof, that's just our goal for the chapter. We're going to this section, we're going to let R and S be non-negative such that their sum is non-zero. Oh, this is part of the lemma. I don't know why they intro some of the lemma before you get to it. That's always weird. Then we have that the norm of H tilde of Rs as a continuous polynomial expounded by our A from our metric to the power of minus R plus S minus 1 times theta. Proof. Let B be a P-Hall set relative to I. Relative to our indexing set I. And we decompose the RS component of the Hausdorff series as the sum of lambda B eta EB with respect to the basis of the free Lie algebra of U and V are indeterminates. Then the size of lambda B is at most a minus R plus S minus 1 theta, which we've already shown in a previous proposition. Moreover, the size of each EB tilde is at most 1 for B in B. We then show by induction on N that for every alternate B of degree n in the indeterminates U and V, the norm of b tilde is at most 1. In our base case, b tilde is a projection of g times g onto g, and so it's trivial. If n is greater than 1, there exists b1 and b2, which are alternates of degree less than n, such that our b here is the Lie bracket of b1 and b2. As gamma sending x and y, these are supposed to be curved brackets, to their square bracket of g times g into g is bilinear. Bilinear of norm less than or equal to 1. The norm of b tilde is gamma composed with b1 tilde and b2 tilde is less than or equal to the norm of b1 tilde times the norm of b2 tilde, which is less than or equal to 1, which gives us our lemma. Alright, on to our second proposition. The formal power series H tilde is a convergent series. Convergent, not how you spell that word. If G is the ball of radius by our norm radius a theta, the domain of absolute convergence of H tilde contains G times G. And the proof, if U and V are two real numbers greater than 0 such that, I guess we'll say that they're in the open interval between 0 and a to the theta, and then the norm of our H tilde of multi-degree R and S component times U to the R, V to the S is at most a theta times UA to the negative theta times R, VA to the negative theta times S. So the norm of our H R comp S on U to the R times U to the R V to the S tends to 0 as R plus S go to infinity. Let H on G and G into G into small g actually, on our ball into G, the analytic function defined by H tilde This isn't part of the proof anymore, I don't know. I didn't format it right. So h of x and y is the sum for non-negative R and S of h tilde sub R and S of x and y, which is the sum for R and S non-negative of h sub R and S of x and y. This is the Hausdorff function of G. By definition. Now, for x comma y in G bracket G, we have that the norm of h tilde R comma S of x comma y is at most the supremum of the norms of the inputs, which gives us the same relation on our little h here, our Hausdorff function. So the second obviously is just a rewording of the first. And for the first, if R is at least 1, otherwise it's trivial, and we have this by symmetry for S as well, h tilde of R comma S of x comma y is at most the norm of h tilde of R comma S times x to the R times the norm of y to the S, which is at most the norm of x times the norm of x over a theta to the R minus 1 times the norm of y over a theta to the S, which is at most going to be the norm of x. In particular, the norm of little h of x and y is at most a to the theta for x and y in G times G. Brings us to our proposition. Just expect our analytic function, which is our analytic function H, makes our ball G into a group with identity going to be 0, and our inverse is going to send x to negative x. If R is a real number in the interval 0 to a theta, then the ball of radius r, centered at 0 of course, is an open subgroup of G. Proof. As h of u comma negative u is 0, and h of 0 and u is h of u and 0 is h of u. We have similar for h. all that's left is associativity. So we'll go to a new page. H of u comma v comma w is equal to h of u on h of v comma w, and L hat of u v w. We have that h tilde of h tilde times identity on G is equal to h tilde composed with, of course, then these two are just going to switch here. We have this commutativity kind of thing. This is in P hat over G times G on G, and we're done. So we have shown essentially that G with the Hausdorff function is a Lie group. Just recall, is a group with a differentiable manifold structure. And yeah, however long this takes, I think we're going to end here because this is the last chapter of Bourbaki before Lie group. So after this, we're just going to finish off Humphreys and then we're done. So this is our last push in this area. So the exponential incomplete normed associative algebras. Let A be a unital associative algebra with a norm sending x to absolute value of x such that the sum is less than the supremum. I did not write the second term in that sum. Is at most the supremum. The product of norms of elements is most the norm of the product is at most the product of the norms, and the size of 1 is 1. And we're going to let A complete be complete with this norm. Let I be a single indeterminate U consider the images of E and L, our power series from before, in P tilde of A on A. Then we have, I'm going to write this as their own lines. U to the n, the norm of U to the n over n factorial tilde is our most A to the minus n minus 1 theta. And the norm of U to the n over n tilde is at most eta to the negative log n over log p by our previous lemma. Hence, our E tilde has radius of absolute convergence of at least a to the theta, and L tilde has radius of absolute convergence of at least 1. For a positive R, let G sub R be the set of X and A in the sphere, the ball of radius R, and we pick G as our G of theta. Then the series E tilde slash L tilde defines an analytic mapping, which we're going to call, of course, EA and then LA of G theta, alternatively G1 into A. We write, of course, to have the exponential of x be 1 plus EAX be the sum of x to the n over n factorial. And likewise, we have log A of x be LA of x minus 1 be the sum from 1 to infinity of negative 1 to the n minus 1 of x to the 1 to the n over n. Then for x in GR and n being at least 1, these of course, we have x is in G and x minus 1 is in G1. So for x in GR, n at least 1, I should rewrite that, I feel like. I don't know why. I'm motivated. The norm of x to the n over n is at most the norm of x to the n over n factorial, of course. Which is less than r to the n times a to the minus n minus 1 theta, which is just r times r over a theta, a to the theta, this whole thing to the n minus 1. Hence EA of GR, EA on G of some R is inside of G of some R, and our logarithmic thing here of G of our ball of some R is inside. Likewise, that brings us to a proposition. Let R be a number in the half-open interval from 0 to a theta. Then our EXPA defines an analytic isomorphism of G sub R onto the 1 plus GR with inverse of the restriction of log A to, of course, 1 plus GR. And the proof is we know first off that E of L of X is L of E of X. These are inverses we see from previous results that E sub A of L sub A of X is L sub A of E sub A of X for X in GR. Then exp A of log of A of X is X. On the appropriate domain, of course, log A of exp A of X is X. We are done. If A's bracket has the obvious bracket, xy equals xy minus yx, A is becomes a complete normed Lie algebra for the norm of our bracket. Well, this is xy minus yx, which is less than the supremum, is bounded by the supremum of xy, and yx, which is bounded by the norm of x times the norm of y. Thus, we saw that the domain of absolute convergence of H tilde contains G times G, and so H tilde defines an analytic function H on G times G into A, with H of X and Y being the sum of positive R and S, non-negative R and S of H sub R S of X and Y. New page. Oh, okay. Well, how long has this video been so far? I'll have to check. We have one final proposition for all x and y in G. The A exponential of x times the A exponential of y is the A exponential of H of x and y. Oh, that's it. In the proof. Well, E of U times E of V is E of our capital H version of hausdorff, U and V. Hence M on 1 plus E tilde, 1 plus E tilde, so our multiplication is 1 plus E tilde composed with H tilde in H tilde of A times A on A with M as multiplication on A, and we're actually done from that. And you know, since we're a little under, they have an appendix here. I'll just cover it for the sake of it. This is just a quick review, kind of a bit too late at this point. A bit of a review on the Mobius function. Let n be a natural number, not 0. If n is divisible by a prime number squared, we write that mu of n is 0. If not, then we write that mu of n is minus 1 to the k, where k is the number of prime divisors of n. Then this function from n, mu from n not including 0 to minus 1, 0, 1 is called the Mobius function. Comes with a proposition. And this they can alternatively write as the multiplicative group. I don't ever assume whether or not 0 is in the natural number, so I always write union if it is and minus if it isn't. Proposition. Part 1. Mobius function is the unique mapping of our non-zero natural numbers into our integers such that mu of 1 is 1 and the sum of all mu d, where d divides n, is 0 for all n in Rn star. For number 2, let S and T be mappings written additively. Oh, no, they're not written additive. I misread, sorry. Of n star into an additively written commutative group. I am really messing this up, right? Group. And then S of n is the sum of t to the d, where d divides n. If and only if t of n is the sum of d dividing n of Mobius of d times S of n over d. So, for part 1, first off, uniqueness is trivial. We can construct the function that meets this formula if it exists. We can construct it inductively with no choices. So we just need to show that mu n, our Mobius function, is this function. So let n be an integer greater than 1. With p the set of its prime divisors. I'm struggling to figure out how to say this. And let n, and we can write n be written as the product for p in our p of P to the VP of N. That'd be the prime decomposition. If D divides N, then Mobius of D is 0 unless D is of the form is the product of P and H, for that is illegible P to the H, P and H, for H being a subset of the prime divisors. Then the sum of D dividing N of Mobius of D is the sum for all H and P of -1 to the cardinality of H, which is the sum for K equals 0 to the cardinality of P of N over K minus 1 to the K, which is going to then be 1 minus 1 to the cardinality of P, which is obviously going to be 0. Now, that's part 1. For part 2, showing it this way. So we have S and T being additive, being mappings of n star into an additive group, satisfying this first equation. Then the second we want to show the term on the right is the term on the left, so we can write the sum of D dividing N Mobius D times S of N over D as the sum of D dividing N of Mobius D times the sum over sigma of delta dividing N over D of our T of these deltas, which is the sum for D times delta dividing N of Mobius D T delta, which is the sum for delta dividing N. Essentially we do the old switcheroo with these two things. Then our D dividing N over D, over delta of Mobius of D, which is just going to be T to the N. And doing it the other direction. So now we want to show that these terms are equal, and as always we'll assume the one on the right and work our way to the one on the left. So we have the sum of D dividing N of TD is equal to the sum of D dividing N, then delta dividing D of Mobius of delta S of D over delta, which is the sum for D dividing N of our SD times the sum of Mobius dividing N over D, delta dividing N over D of Mobius of delta, which is our Sn. And that's our Mobius inversion formula. And hopefully that padded out the video long enough to make it full length. Yeah, after this, we are now on, I'm going to check here because there's a whole bunch of exercises and stuff which I'm working my way through in my own spare time, and I advise you do the same. And there sure are a lot of them here. And yeah, then we're on to Lie groups in this book as well. So we're almost done in that setting. Yeah, thanks for watching.